All right, so now business begins. So when ICAS was founded in 1957, it received financial support from the Daniel and Florence Guggenheim Memorial Fund. The Guggenheims were great admirers of aviation. In fact, all the major universities in aeronautics in the United States are actually Guggenheim schools. They were all founded between 1928 and 1932. So the idea of this memorial fund was for the promotion of international cooperation in the aeronautical sciences. So they were supporting ICAS from the very beginning. So in recognition of this assistance, ICAS inaugurated the memorial lecture that we are about to hear today. This prestigious lecture is by tradition the first lecture of the Congress and is given at the end of the opening ceremony. Interesting enough, the very first Daniel and Florence Guggenheim lecture was delivered in the first Congress in Madrid by Professor Theodor von Karman himself, the driving force behind the creation of ICAS. And interesting again enough, his subject was some significant developments in aeronautics since 1946. The Distinguished Lectureship Award is intended to recognize and honor an eminent professor, engineer, or scientist who has made a significant contribution to the progress in aeronautics throughout a long and productive career. Also, by tradition, the lectureship is awarded to an individual nominated by the hosting member society. So in this case, it will be a representative from Italy, who is usually a national of that country that the conference is taking place. So this year, your Daniel and Florence Guggenheim lecture will be presented by Dr. Roberto Cingolani. And I have a few notes about Roberto. Roberto is a physicist by training, an academic, and an industry leader who has had a very great and accomplished career working for universities, companies, and government organizations. He has helped drive innovation and technological advancement in Italy throughout his entire career. So I have a few more details to help us appreciate the ethos of our speaker, who will be presenting to us next. In 1985, he graduated from the University of Bari with a degree in physics. In 1989, he was awarded a PhD in physics at Scuola Normale Superiore in Pisa. He was a staff member at the Max Planck Institute in Stuttgart from 1988 to 1991. After that, he joined the University of Salento in 1991, where he was appointed full professor for experimental physics. He was a visiting professor at Tokyo University and at Virginia Commonwealth University from 1997 to 2000. In 2001, he founded the National Nanotechnology Laboratory of the Istituto Nazionale per la Fisica della Materia di Lecce. In 2006, he founded the Istituto Italiano di Tecnologia, of which he was scientific director and chief executive officer, until his appointment as Chief Technology and Innovation Officer of Leonardo in 2019. Then he served that role until 2021, and in February of that year, he was appointed Minister of the Ecological Transition in Mario Draghi's Italian government. Since 2023, Dr. Cingolani has been a Chief Executive Officer and General Manager at Leonardo. He has served as technical advisor in different panels for the Ministry of Research and University, including the Commission for the Selection of the Centers of Excellence and the panel of experts for the drawing up the National Research Plan, as well as for the European Commission, especially in the fields of nanotechnologies, new materials, and new production systems. He has received many national and international awards, including the honorific title of the Order of Merit of the Italian Republic, from the President of the Italian Republic. He is author and co-author of more than 1,100 publications in international journals and holds over 100 patents in material sciences, semiconductor technologies, nanotechnologies, and so forth. So it is a great pleasure for me to introduce Dr. Roberto Cingolani to present the 2024 Daniel and Florence Guggenheim Lecture.
So, hello everybody. Thank you for this invitation and opportunity. When I was awarded this opportunity. I thought this was because I fly on average 300 to 350 hours per year, and I thought this was my biggest contribution to aeronautics. But then, of course, more seriously, I've been thinking to the 30 years career in technology that I spent before joining the company. And I think some of the technologies have been developing and studying over the years, including transparent displays, high power electronics with gates in the range of 20 to 4 nanometers. Stuff like that could have definitely been used in some of the most advanced technologies that are flying around on the earth at the moment. However, now, since very, very few years, as you heard at the very beginning, I'm dedicating all my time to Leonardo. Leonardo is a multinational company. It's dedicated to aerospace and defense. It's among the top 10 in the world, about 55,000 people on over 100 countries. The domestic markets are, of course, Italy, and then US, UK, Poland, and the others are essentially satellite markets. The revenues are in the range of 17 billion this year, growing quite fast. And the key action, the streamlines are aircrafts, helicopters, cybersecurity, space, electronics. So it's a rather transversal company. So the message today is how to transfer this rather transversal point of view to the world of aeronautics. We are experiencing quite a big change in technology, but also in society. And I believe that this is something that deserves some technical discussion. So first of all, I'd like to share with you a few key ideas that are totally heterogeneous. So what is happening over the last years is that several new technologies from the civil market are becoming also game changer in the defense. So this is a non-exhaustive list. Artificial intelligence, for technical people, is basically a combination of algorithms, computing capability, and data. Robotics and autonomous systems at large can be defined as the capability to build platforms that are able to actuate physical motion, no matter whether these are autonomous or non-autonomous. Internet of Things is actually the sensor network that we use commonly for many applications, including interfacing to autonomous systems, to robots, and could be used also to fill with data machines that produce artificial intelligence capabilities. 5G and satellite connectivity, it's the nervous system of the new technology environment, is actually how data are transmitted from sensor A to a receiver or from a robot to another robot. So therefore, this is our communication network. Cybersecurity is becoming more and more important because if you transmit data, you want those data to be quite well protected. Intercepting data means blocking everything. Geospatial services are actually what we need now for global monitoring, for positioning. So nothing that happens now in technology, nothing that happens now in technology could be possible if we didn't have very precise global positioning, monitoring, and capabilities that are provided by satellite services. Cloud services, this is what we call in biology the connectome. So the place where you have all your data, and these data are cross-correlated and eventually analyzed by a machine that makes the computation. And finally, virtual and augmented reality is just a simple interface to communicate with the humans. We need to have a physical perception of what happens in the digital world, and this is the virtual reality or the augmented reality. Now, let's go to the other side of the life, which is the war. There are 55 conflicts at the moment in the planet, and I want to share some tricky examples of what happens in unpredictable threats that can be seen every day. October 23, Hamas attacks Israel with commercial drones. Typically, the cost is a few $1,000s per machine. Each drone carries maybe 1 kilo of C4 drops on a tank that costs 10 million euro. February 24, Ukraine attack, Magura V5 drones, it costs $750 destroying a ship which is worth of a fraction of a billion. April 24, Iran attack with drones, cruises, ballistic missiles, estimated 120 million investment for this attack. The Iron Dome of Israel neutralized the threat, but the cost is approximately 1.5 billion. What does it mean? That defending is getting 10 times more expensive than attacking. That's not good if you want to have peace and if you want to have a safe society. This is because those are too small or too fast threats, cannot be predicted, cannot be computed in real time, so we don't have defense. We are weak. Therefore, we have to ask ourselves where technology should go to make a country safer under attack. Another example is the Houthi attacks in the Red Sea. This is something, the third element I want to add to this discussion before entering into the technology. Small kamikaze unmanned boats, $50 dollars cost each, so very cheap, or the Shahed loitering drones, again, $50,000 each, combined with cruise and ballistic missiles, which are more expensive, they're just paralyzing Western society, almost paralyzing. You see from the pathway, the blue and the red lines, you cannot go through the blue line in transporting duties from one point to another point. You have to go through the red line. That means drop in trade volume by 50% in the Suez Channel, shipping cost increasing by 180%, shipping time increased by 10 days on average, insurance rates for the duties times 3. That means the average container transportation is going to cost approximately $3,400 per ton versus the previous $1,200 per ton. So, why am I telling you this? Because in general, this unprecedented war situation that we're experiencing now, only after the Second World War, there were more than 50 conflicts in the planet. What we are living now is comparable to what happened in 1945, is going to put under discussion our security at very global scale. So not only defense in terms of war, that everybody knows since thousands of years, but also food insecurity, energy insecurity. You've seen after the Ukrainian war what happened with the gas and with the price of electricity. And more in general, a class of problems, social problems, such as healthcare, transportation problems, financial services under threat, social stability, supply chain, social stability, for instance, when there is an attempt to intervene into the democratic elections in a country. Other essential services are under discussion, are under threat, and this is what we call the cybersecurity at large. You can digitally attack a country without shooting a bullet, creating a serious problem to that country. So, lesson number one that we have learned very recently from Ukraine, from the Houthi, from what happens around the world, is that we should start thinking seriously in a different way, from defense to global security. Global security will exist. There will be a need of global security even after the war will be finished. And we all hope the war will finish as soon as possible. But the global security will be needed anyway. The second lesson is that clearly it's no longer a matter of bullets or weapons. It's going to be much more complex. It's going to be a matter of bytes, data. That means you have to monitor what happens in real time. You have to compute in real time what happens in a specific area. You need a digital continuum of data where you understand what happens. You have to make forecasts. You have to predict what happens. And today, predicting what a small drone is doing or an hypersonic missile is doing is very difficult. So that means that we don't need weapons, or at least we hope to need less and less weapons in the future. We need data and computing capability. If you don't accept this, it means that you don't want to have security in the future. So this is, and I go now to the more technological core, and I apologize since the very beginning because maybe I cannot share or disclose too many details. You imagine this is anyway kind of company, not confidential, but close to confidential. I hope I can answer all your questions satisfactorily. But anyway, this is the picture that's going to be developed over the next few years, and it's a very urgent picture. This kind of pancake that you see there, we call the volume of the digital continuum. Their data are in the air. We have to work on a multi-domain approach. That means air, so aircraft, helicopters, land, tanks, infantry vehicles, maritime, so ships on the marine, space. They have to be capable to talk to each other, which has never happened before. The new electronics is the glue of this technology. You need a specific electronic capability to make all those domains to talk to each other. Under the digital continuum volume, you have a supervisor, which is the space, the satellite services, monitoring, positioning, and so on and so forth. This is equivalent to the sentinel that in the 18th century was on the top of the hill walking around the flatland. Now, data are exchanged among the platforms. So this is a cross-domain situation. Data are exchanged, and there must be an AI that takes in real-time decisions on what is the best, fastest, more effective response to a specific threat. You've seen this when the Houthi were attacking in the Red Sea, and there was a combination of weapons from different countries that were responding selectively to stop the Houthi attacks. And those were aircraft, combat aircraft, were ships, were other drones, and so on and so forth. That was a real-time decision done on a very simplified situation. But in the future will be much more complicated. So the data that the platforms are exchanging should be protected. So that specific data continuum has to be completely cyber secure. Otherwise, there will be no hope to succeed. You must have a very high computing capability because trajectories, impact times, and everything should be computed in real time to be effective. And you need data to be collected and exchanged with the computational machines in real time with very fast interfaces. So the enablers are the digital continuum, so the volume of space where you control all the data, the cloud, where those data are stored and processed, and this is in the petabyte range now to be really effective, so 10 to the 15. Computing power in the petaflop, so 10 to the 15 floating point operation per second is the minimum level that allows you to think in this way. You need resilient broadband communication. You need digital twin, because if you want to simulate and calculate what happens when a rocket or an aircraft is attacking, you must have the digital twin of that specific machine. So not only yours, but also those that are from the threat, from the enemy. And you need artificial intelligence, ultimately connecting, choosing, deciding, and launching the defense. The key features on this side, it's the multi-domain interoperability. The concept of interoperability means that we have to put together data that are from the land, from the sea, from the air, and we have to be ready in real time to extract information from those data, to process those data, and to make decisions. All your platforms, aircraft, ships, helicopters, they have to share command and control logics and principles that are compatible to each other. Today, it's impossible that an helicopter talks to an aircraft that talks to a ship that talks to a tank, because the command and control are different. So you have to change completely the approach. Modeling, simulation, and training have to be extremely effective. The economy in terms of time consumption of the modeling, of the predictive modeling, is fundamental here. You need very strong mathematical background for that, very strong algorithm background. Global monitoring means space, especially low orbit constellations, because clearly you cannot afford for long latency times. Latency time should be very short. You make a decision in a fraction of a second, like if you were a human. System of system architectures. this is in aircraft is possibly ahead compared to the other domains, but system-of-system architecture means that you need to have a father or a mother platform controlling drones and controlling other machines with a swarm intelligence so that this can be controlled and operate in an orchestrated manner in full synergy. Everything cyber resilient, I told before, because if we intercept the data, of course, the machine breaks. And of course, most of those systems will be autonomous, so crewless, very likely. Now, this is where top industries are going. This is where technology is going. This is where everybody designing electronics, cybersecurity, space applications, platforms, aircraft, tanks, ships have to land at the end of the next decade. What technology can do today? This is the plot over the last, say, 80 years or so about the computational power in floating point operation per second. I don't want to oversimplify. I'm sure there are very expert people in the room. Let's say operation per second, okay? Not really true, but it's okay, it makes sense. So with the exponential growth of computational power, when we landed on the moon, the computer that was controlling the LAM was very likely comparable to an iPad today. Of course, today we have much more powerful machines, and we're approaching, there are few machines in the world, few supercomputers in the world, the exaflop scale, 10 to the 18 operation per second, which is, by the way, comparable to the human brain capability. But as I'll show you in a minute, this is not enough. It's not only brute force computational capability, but that is the first step. You need a lot of computational capability. We'll see, we need more. So only lately, we reached routinely the petaflop capability, 10 to the 15, moving towards the 10 to the 18. And now it makes sense to talk in terms of artificial intelligence. Before, I was not intelligent enough. If you want to see this in a more clear term, look at this plot. This is funny because it contains a lot of information. So first of all, the scale is how many millions instructions per second a machine can conduct with $1,000. Guys, I said million instructions. That is more than operation. Instruction could contain many, could need many operations. It's a very qualitative approach. Today, to be in the petaflop, you need maybe $100,000. But the hope is that by 2030 to 2040, we can be in the range of $1,000 for something like a petaflop equivalent operation per second. Now, the tricky thing here is that nature, or well, I should say evolution, has taken 500 million years to evolve from a very simple organism to something like a primate or a human. But if you want to see, in the mammalians area, it took approximately 200 million years to go from the mouse intelligence to the human. The dry learning, the silicon learning, it took 70 years from the discovery of transistor to approach the exaflop computational capability. I mean, if you want to be more precise, Sapiens, that was a bit more than a monkey when it appeared on the earth 130,000 years ago, was, as I said, a monkey, and it took 130 years to become an advanced creature. Silicon, it took 7 years. I mean, silicon is a product of humans, of course, but why this happens? Because it not only the computational power, but also the connectome, the capability to manage data, has been increasing correspondingly. And this is a very important point because it's impacting on our technology. This is just an example. Look at the last two. Size doesn't matter so much in terms of brain. Elephants have brains that are in the range of 3 kilos. Humans have brains in the range of 1.2 kilos. But the number of neurons is approximately 5 billion neurons for the elephant, 16 billion neurons for the humans. Each neuron is interconnected to many neighbors, so that in a human you have 10 to the 16 synapses. That's the connectome. That is what allows you to put information all together and to interconnect and process them in parallel. If you don't have the connectome, it doesn't matter that you have a big brain. Therefore, if you have a big computer, it doesn't matter that you have a big computer without strong big data capability, big data analysis capability. So when you make a technology choice, you have to mimic nature somehow. So you have to build an expert system. So the number of neurons and interconnections, 10 to the 16 in humans, correspond to the petaflop and petabytes processed by a high-performance computer that must have a very fast interface between the cloud and the machine. There is no point to have big data, computer, and a single wire that connects the two, because that will be the bottleneck, and the machine will never be fast enough to make a decision in real time. So now we go to the real science. Not that this is not real science, this is biology, is wet science. Now we go to the hard science. If you can develop machines like those, then you can precisely simulate or model the behavior of floating objects, the aerodynamics of cars under very extreme conditions. Today we're developing new drugs, and specifically chemotherapeutic drugs, just making exact simulation of a cluster of atoms in a protein, where there is a mutation, for instance, with an active principle which is simulated exactly for approximately 2 nanoseconds in molecular dynamics, and you can really simulate how the anti-cancer drug impact onto the mutation into a protein, for instance. That means a shortcut in the drug development in the range of 10 years, saving money for millions of dollars or euro, whatever. And this is because you have high power capability and big data and very powerful algorithms. Similarly, you can make advanced fluid dynamics and force field analysis for a wind generator. So you see, you can do almost everything. Once you predict, you predict. You can develop microscale thermal analysis of high-powered devices. This is not thermal conductivity, because it's not the diffusion equation. This is real microscopic cooling capability. You can develop cars digital twins. You can develop aircraft digital twins. And if you have those, you can make autonomous driving. You can simulate a combat scenario. You can simulate multi-domain operation. What you need is a lot of data, high power capability, fast interface for cloud computing. So this is how it came out. The reason why cars have been designed with a very high pace recently, and every 3 years you get a new model, it is 90% of the job is done digitally. With aircraft, we're moving in the same direction. At that point, if you have the digital twins of everything, you can simulate a totally virtual system, like a combat scenario or traffic scenario, whatever, and of course you become predictive. Now, it's not relevant today, but the trend is that in about 20 to 30 years, we're going to have the first digital twin of a human, 10 to the 27 cells. And maybe in 40 years, the first digital twin of the planet Earth. And then you will see that diseases, earthquakes, climate change will be entirely predicted in a quantitative manner. But for that, we need to escalate more and more on computational power algorithms and data analysis. So, with the recent advancement that came from the GPU technology that has been outperforming, as you see in the plot on the top, the GPU have increased much faster than the CPU, the capability of our machines. The combination of high-performance computing, algorithms, and cloud computing today provides to our industries and you guys, to your community, high-fidelity simulations that were absolutely impossible 5 years ago, real-time simulation, including, for instance, simulators, training of pilots or whatever, combat scenarios, as I said before, and complex realistic simulations. As an example, this is what we did in Leonardo. Actually, we started this started about 4 to 5 years ago. There is a dedicated machines that is growing every year. This machine has, of course, very high computational power, very high capacity data management system, but also, which is the main characteristics, a very fast computer memory interface that makes the machine extremely flexible and quick in decision-making analysis. To give you an example, you see on the left the Whirlwind. That was the first high-performance computing developed in, I think, in the 60s and 50s. In MIT, 20,000 operations per second, 4 kilobyte memory, 150 kilowatt power, 300 square meters. Today, all this is in your pocket. But at that time, that was the standard. If you compare to our machines now, 5 millions of billions operation per second, 20 petabyte memory, 1/2 of the extension, only less than 3 times the power, which is going to decrease over the years with improving technology. And on top of that, the speed by which the memory talks to the computer is so fast that you basically have no latency in the processing and decision making. An application, I cannot say very much about that. I mean, this is I'm sure most of you know the 609, the tilt rotor technology that we developed. It's an aircraft that can rotate the engines, so vertical taking off, and then tilting by 90 degrees the engines, flying like a normal aircraft with wings, and then upon landing, again, tilting the engine and going down. Okay, this machine has no rotation for the rotors. You can change the angle, so it cannot land like an helicopter. So to land on a ship, on an aircraft carrier, has to make a specific movement, and you have to calculate exactly the fluid dynamics, the force vectors, force fields, and everything. So now we are able to simulate completely. This is only a part of the simulation. I cannot show everything. The aircraft carrier is included in the simulation completely, and those are the force lines of the engines that allow the machine to land on the aircraft carrier by a spiral motion, almost vertically. We did this. It took a lot of computational power, a lot of data, and then we made the test, and the test was 100%, a real test with the real aircraft on the real ship. It was 100% successful. So that machine that takes off and lands vertically and then flies like a normal aircraft, much faster and pressurized, can actually land vertically on a ship carrier, despite there is no control of the inclination angle of the rotors. More examples. This is something we've been doing. The 139 helicopters, which is one of our strong horses in the production. This is called the Dorian Gray program. We have collected data from 1,200 helicopters around the world, 12 years of flight history, approximately 1.8 million hours of flight, and approximately 50 terabytes of data have been processed by an AI. And actually, this has allowed digital services for predictive maintenance. That means you don't say to the owner of the helicopters, every 1,000 hours of flight, you have to go for the technical assistance. This is done specifically for the flight condition of the helicopters, the use terms, the scenario in which the helicopter has been operating. The predictive maintenance is a strong asset for the customer that is using helicopters because it's an intelligent maintenance. You save money, time, it's safer. Flight operation optimizations, needless to say, because you start understanding so many things after analyzing all those data. New design approach for the next generation platform, because those platforms are evolving continuously. And of course, improvement of the CO2 emission, because you learn so much stuff from that analysis that you can really improve the capability of the machine. Actually, that was a simulation with 140 free parameters. So those are 100 variables that are controlled by the algorithms. I mean, for you to understand, in some of the most complex problems, we go towards millions parameters, billions parameters. And if you want to make, for instance, digital twin of a human to resolve diseases, to understand and predict diseases, you have to go to the trillions parameters. And for that, you need hundreds of exaflops. So this is the way we go in digital twin in any technology field. Something similar was done on the 346 and C-27J. C-27J is a transporting aircraft. The 346 is a trainer, supersonic jet, very high performances as a trainer. In that case, it was a 173 free parameters simulation, 80 transporter and 90 trainers. Now we are extending that technology to all the other families, ATR, Eurofighter, much more complex, Euromail, drones. You understand, this means that you become totally predictive. And of course, you can improve safety, quality, performance, and provide much better services to the users. Along this track, we go to the GCAP. I'm sure most of you have heard about GCAP, I'm sure. You know about the 6th generation fighters? Can I see how many of you knows this? All right, okay. So for those who don't know, and for the students primarily, today we are using state-of-the-art machines are 50 generations, like the F-35, or 4th and something generation, like the Eurofighter. The F-35 is a stealth machine with high computational capability, strong network sensing, maybe difficult to communicate with other platforms, not interdomain yet. The 6th generation machine is supposed to be a stealth machine with very high performances, but capable to control a swarm of 30, 40 drones, so that this is not a single aircraft, it's a fleet. There is the mother or father aircraft, with a big one, and 40 drones that are controlled, having different functions. Recognition, surveillance, attack, sacrificial, defense. So imagine it's the equivalent of an aircraft carrier. You don't take off with one aircraft, you take off with an aircraft and 40 drones. So this is basically a flying high-performance computer that has to be capable to develop swarm intelligence to control the 40 drones in a very complex real scenario. This is now under development in a consortium, Leonardo, BAE Systems, and Mitsubishi, but there are other competitors, of course, around the world. It's $100 and more billions dollars program over maybe 10 years or so, so it's something quite big. The concept of the system of systems, where an aircraft controls another 40 adjunct drones, is that you need the stealth combat air platform. This is an aircraft, so you need, again, mechanical simulation, all what you do for a state-of-the-art machine. You need to make fusion of data and sensory data, multispectral sensory data, because this machine will have all kinds of sensors embedded to control the drones and to control the combat scenario. You will need the next generation effectors, because the performance of this machine are superior to what we have now. Advanced power and propulsion. You have to develop the drones with their different capabilities. Each drone is essentially an aircraft itself. You need advanced training, modeling, simulation. This is nothing you go and pilot. You need a lot of training because you change completely the approach compared to a standard pilot. You have to govern a fleet. And of course, all this exists because you can develop digitalization, AI, high-performance computing, advanced digital twin technology. You need a common working environment, a kind of headquarters where you monitor the fleet, autonomy, security. So you see, this is really the future. And I can't say it has nothing to do with the aircraft technology. It needs the best of the aircraft technology, plus the best of artificial intelligence, plus the best of data analysis and sensory fusion. So this is the most concentrated cluster of technology that you can think of today. And of course, it has to talk to the satellites, because in the combat scenario, the supervisor will be a satellite. Okay, this I've told already. Least but not last, I'd like to tell you the dream is that we should be able to move soon some of our computational capability in the low orbit. So what we call the space cloud. Today, the satellite observes, send the data downstream to the Earth, somewhere in the headquarters at the surface, data are processed, then they are bunched back to the satellites, and this takes a bit of time. But we want zero latency, like a human. I decide instantaneously, by instinct sometimes. So having delocalized computational capability and data capability in the satellite, in the low orbit, with low latency, means that we get much faster. And especially the satellite that is giving the service that supervises everything happening in the digital continuum, in the cross-domain that I've shown you before, that will make our capability much higher than the competitors. So this is good for military space operation, for multi-domain operation, but also for economy, for European space sovereignty, whatever. I mean, this is dual. It's for everything. Global coverage, 24/7/7. Reduce ground dependence, because you make at least the preliminary calculation analysis is done in orbit directly. Reinforced data security, because data travels much less. The point is now the current electronics, high-performance electronics, capable to be in orbit? That's a technological challenge. Many companies together, this is nothing we can do ourselves, nor NVIDIA can do itself. We need to put together the know-how, because it's a very cross-disciplinary approach, but this is where we have to go. So let me tell you the conclusion. For me, no AI, no HPC, no high-performance computing, no data, nothing of that means no party. We don't go far. We don't progress enough. We can be slightly faster, slightly greener, but we don't go far. We need much more. And to let you think about the size of this challenge, imagine a swarm of 100 drones. It's nothing, 100 drones. The total computational power that is required to manage the swarming of the drones is given by the number of drones times n times the power which is needed to process sensor data at local level, the power for real-time communication and synchronization among the drones, they have to move in an orchestrated manner, and the power for autonomous decision, machine learning, planning, and so on. So the estimate at the moment for such a scenario is something like 350 tera operation per second. And this is nothing. With 100 drones, small drones, you don't do much. So this is the challenge we have in terms of computational power, data analysis, acquisition, analysis, and exchange. And everything has to be with almost zero latency and in a totally cyber-secure environment. So I think this is the real challenge. And I believe your community will be more and more involved in this, because without this approach, you just have a single aircraft flying, and the others might have a lot more technology simply to stop you. And I don't think this is a good scenario for global security. Thank you very much for your attention.
Okay. Thank you very much. We're going to have time for questions. And again, please ask questions that they're not poking too much into the secrets of the company, okay? So if you can recognize yourself and say who you are and then ask your question. There are, I think, microphones running around. Yeah. We need someone to be brave enough to start. There's a microphone here on this side. Yeah, you go.
Hello, Carmel Matias, Israel Aerospace Industries. So all these computer power, you talk about the aspect of the product. Certainly there will be aspect for the working effort. How do you vision, already nowadays, there is kind of no need for static testing because power is enough for computer, but still there is need for fatigue testing. Too much information there. So two questions, how do you vision no need for fatigue testing also for power of computation? And a more hypothetical question, how do you vision no need for engineers?
Okay. I believe that for the time being, since we are developing, since we are at the very early stage of the cross-domain interoperability, you're right, the computational capability we have is enough, but my forecast is that in 2-3 years, we will need to grow. Anyway, the electronic companies and the computer capability is growing much faster than defense, and so this doesn't worry me. Even if we need more, we should find it. What worries me a lot is the lack of STEM people. Because actually, to answer straight to your question, which is that I absolutely agree, we need brains, we need minds. So right now, for instance, I see in my company, we built up a large-scale AI center connected to this high-performance computing facility with a cloud computing facility attached. It's about 200 people. They're no longer enough. Space is growing exponentially in this area. we need more, we don't find them. To give you an idea, I mean, about Europe, but I think, I don't know, maybe in US is slightly better, I'm not sure. Only Leonardo has a plan to hire something like 27,000 people in the next 5 years. Let's say 10,000 are just replacing people who retire, okay? So the net is going to be 17,000. 60% are kind of engineers, developers. So let's say 10,000. Those are STEM, science, technology, engineering, mathematics. Italy produces approximately 30,000 STEM every year. Of course, Leonardo is one company, maybe the biggest, but we have a lot of companies, and we don't have enough for the demand. Now you could say, go and hire from France, Germany. They are like us. I don't know. I mean, I think also in Germany there's a problem with the STEM people, right? In France, I'm sure too. So ultimately, we should not compete on our brains in Europe because we are all in the same continent. In the past, we were able to hire very good Chinese engineers, Iranian engineers. Now the situation is very complex. So we cannot rely on international, intercontinental relationships. So we must make an effort, a serious effort at domestic level. Domestic means continental level, to boost the production of STEM brains. Because that is the bottleneck, not the computational power, not the infrastructure, even not the money. The bottleneck is the brains. And this is my main concern for the next few years.
Thank you very much. I think there was another question right there.
Alessandro Giacotto from Aeronautics Institute of Technology from Brazil. Roberto, thank you very much for your presentation. On slide 8, where you show the DOM and how all the assets interact with each other, you put an emphasis on AI, and then later on your presentation, you also mentioned how important is the latency. So some authors still say that human has to be kept in the loop in the decision making. Some authors defend that the human brain shouldn't be in the loop anymore, should be AI should take the decision. What do you think? Do you see a future where important, maybe attack or defend decisions are taken by very fast, very well-informed AI? Or do you still see room for the human brain to take the final decision? Thank you.
Okay, generally speaking, as you know, this question is a bit borderline to the ethic considerations about AI. So I will answer personally, not as a representative of a company. I think supervised AI is by far better than autonomous AI. Generally speaking, there are infinite possibilities in any scenario, not necessarily war, whatever. And I think that AI still is a very powerful tool in the hand of the human to make faster decisions. Now, passing time and developing the technology, your AI can be more and more expert, more and more reliable, so you can progressively give the chance to the AI to solve, to fix problems that are getting that are standard but less standard than the previous one, let's say. So you can increase the level of difficulty that the AI can approach in autonomous. This is exactly what we do with the growth of humans. I mean, your children get more and more responsibility the more they get mature and expert. I think we have to make a clear point. Imagine in the scenario I've described before, where you have a Navy force, Air Force and land forces, submarine forces. You know that those forces, those armies have their own data, and of course they don't want to share, clearly. So you need an AI that cannot be generative, simply generative. You need to train an AI so that the AI has access to all the information clusters without putting the cluster in contact to each other because of confidentiality. But in the meantime, having a clear vision of all what happened. This is what we call the federative AI, which is much more difficult and slightly slower to train than the standard generative AI. So right now, people are talking about AI simply. Best things are done by generative AI, but we already know that we have to go towards the federative AI, which is next level of the video game, let's say. So by the time you can develop very strong, fast, reliable federative AI, you can possibly train your AI in a very advanced way, and you can rely on its decision better than on the decision you get today with a let's say, simple generative AI. But this is something we have to see in the course of the next years. Giving an answer now, it could be risky. Don't forget that, as I've shown before, in 70 years, we went from nothing to making decisions. Ourselves, we took 130,000 years. So never say in principle the technology should not go there. Just watch it, study it, and make the decision at the right point after making careful testing and analysis. And yeah, so a prudent approach.
Thank you, Roberto. Thank you for your question. I'm looking.
There's a gentleman there.
Over here, right there, Pradeep. Yeah. Can you introduce yourself?
Thank you. I'm Pradeep Raj from Virginia Tech. And first of all, thank you very much for sharing your thoughts. My question is, did you comment on the role of quantum computing in your vision? Thank you.
Okay, you're touching my deepest sentiments because, you know, when I was a full-time scientist, it was 1993, I had my first European program on quantum bits fabrication. I was an hardwareist, so it was a real bit, not theory. So yes, of course, on one hand, I should say very frankly, I started with quantum computing in 93, 94, and after 35 years, we are still talking about quantum computing, but you know, this is still far to be a block of technology to put here and makes its job. It's progressing. Quantum simulators are very, very good, I would say, but those are silicon computers that operate mimicking a quantum system. They have advantages. I'm not sure they are fast enough and for the applications I told you, because we need almost zero latency time. But let me answer you with a general scenario. Tomorrow, somebody invents the quantum computer that does not need any low temperature, no extreme cooling, which is cheap, can be programmable very easily. At that point, I expect such a speed and such a computational capability that everything I told so far should be done by a machine that is big like a shoes box with very little energy consumption. If you give me this, you make me the happiest man in the world. But yeah, at the moment, there is no indication that this is the case. But for sure, the community should insist in developing quantum computing. If something will come in the future, this will be a monumental breakthrough.
Okay, thank you. Right, yes, right here.
Thank you very much for your presentation. Sorry. Yeah, because I think that artificial...
Introduce yourself first. Introduce yourself.
Okay, I'm from AVIC, from China. My name is Chen. Yes, I want to ask that you know that the usage of artificial intelligence, they are maybe out of control of human people if we proceeded too fast. And you know that there is some kind of dialogue between the USA and China. They talk about artificial intelligence usage. So, you know, as an important part, like European Union, do you know that is there any kind of effort in the industry or in the government to communicate between the three parts? Because, you know, they are the three most important parts. So do you think that there is a need, and is there any kind of effort doing that? Thank you very much.
Yeah, thank you very much. This is a very interesting question. Generally speaking, I think that saying that artificial intelligence is out of control is a little bit too much, in the sense that you can switch off the computer and this is over. And this is the advantage of everything driven by a silicon machine. So no AI can actuate itself, because anyway you have the supervision of the switch. What can be a problem is that some of the algorithms, like the deep learning, are unsupervised, so you don't know exactly how they operate, and you just get the result without knowing exactly how this result was accomplished. That should be carefully pursued as an approach. We should see what's going on in the algorithms. I think it's very important that big countries get an agreement how to use it. AI is a very general facility, but it can be a weapon, clearly. And I think as for all weapons, there should be some code of behavior by the big countries, but without having the idea that it can be completely regulated. In this respect, I would like to mention that Europe, for instance, has pursued a totally different approach. We first make the rules, and then we make the cars and the roads, like making, the driver conduct rules without having cars and roads. That was the opposite approach. I don't think it was very successful. A wild use is also not very successful. It's good that companies and states talk, but in the meantime, I am less worried about the fact that AI can become dangerous and autonomous. This I find more science fiction than real, to be honest. I hope I'm not wrong.
All right, thank you very much. Right here. Mary.
Thank you. Hello, I'm Murray Scott from Advanced Composite Structures Australia in Melbourne. The context of my question is Australia is investing in a loyal wingman program known as GhostBat. You mentioned your sixth generation fighter program will operate with 40 drones. You didn't say anything further about the drones, but I think the expectation is the drones are going to do the mission. Could you just perhaps expand on those 40 drones rather than just the fun bit, which is the new fighter?
Okay, so maybe I cannot say too much, but 40 was the order of magnitude of the drones that could be controlled in the swarm, having different functions, as you said. Yes, they should operate. Basically, they should make the mission is demanded to the drones, whereas the GCAP, the aircraft, should be a sort of flying headquarters that is quite safe, and possibly not on the hot battlefield. Now, to enter a little bit more in the details, you understand that if the GCAP or the mother sixth generation, the father sixth generation machine, it's a highly supersonic machine with very long range. Now the question is how the drones, from where the drones take off. If they are under the wings, of course, they don't have the range, the speed, the capability. So I would exclude that. So I would better consider the drones in the adjunct as aircraft themselves, but they cannot be as expensive as the GCAP. So being stealth, big, with long range, super performances. So maybe they have to take off from airports that are close to the let's say, war area. This is absolutely not yet clear. It's been under discussion. I think for this reason, there is anyway good room, technologically speaking, good room for developing a sort of universal adjunct that can be used by any sixth generation fighter or by any aircraft which is equipped with high performance computing, big data analytics connected to the satellite with a cyber secure network. So we are in the very infancy stage. I think your question is too expert for the understanding that, or at least for the clarity that the community has about what the real sixth generation fighter should do.
Thank you, Mary. Okay. Who's next? Right here. Bruno.
Bruno Stoufflet, I'm in the Air and Space Academy in Europe and former CTO of Dassault Aviation. So you recalled, and it was very convincing, that low sophisticated threats can be very damageable threats. Low cost threats can be very damageable. So we could think that the future is to develop low sophisticated threats that could saturate defense rather than develop a very sophisticated new fighter with drones costing $100 billion. Or maybe the future is a combination of the two. I would like to have your opinion about this.
Yeah. The low cost, the low sophisticated drones and attacking systems turned out to be very effective very lately. But I think the countermeasures are being developed quickly, like electromagnetic shock weapons, lasers, laser guns. So I have the feeling that in let's say 5 to 10 years, there will be several countermeasures. But of course, technology is fast. So by the time we develop those countermeasures, there will be something new. I think very likely a hybrid combination of top sophisticated technologies and low cost technology will be always the case. Today we call them drones. Maybe in 10 years will be something different. But I suspect that this is kind of inherent to the field.
Thank you. So far, 6 questions, 6 countries, okay? So going to Canada next, okay? 7th first, 7.
Thanks very much. Philip Ferguson, Canadian Aeronautics and Space Institute. You mentioned some of the challenges that we have in front of us in terms of international cooperation, but I think that it's safe to say that problems as important as you discussed today cannot be addressed by a single nation. Sure. We have got an entire room today full of many different nations. What does ICAS have to do in the future to get past some of those challenges, the political challenges that we have that are preventing different countries in the room today from working together to solve those problems?
Thank you. This is a very, very, very good question. First answer is as European and as CEO of a European multinational company. The Ukraine war demonstrated that Europe is tremendously fragmented. We invest approximately 1/2 of what the United States invests in defense, okay? So we're not, maybe we're the second investor, maybe the third in the world. So technically, we should be quite strong. But we are so fragmented. We have 12 tanks, maybe 10 aircraft. So, everything is fragmented and duplicated. We don't concentrate the effort. Now, if you see, I have numbers, I go by memory, but the procurement in 2023 for Europe was some 110 billions. For US was maybe 250 to 300. But US was was allocating that procurement investment onto a dozen of platforms. So let's say 20 billions each per year. Europe was allocating those 110 billions on 30 platforms. Only the tanks are 5, 6. So, on average, 3, 4 billions per platform per year. That means you will never be competitive. And when you want to help a country, like in the case of Ukraine, you give the same weapon, 155 millimeters caliber, but the bullets are different. So this means that fragmentation is counteracting for sure. Number one, which is always true in technology, by the way. But in the case of defense, people are dying. And this is twice a big mistake. If I compare now, if I widen the horizon of my answer to the global system, to be strong partners of the NATO alliance, we have to be, as Europe, reliable and strong. But otherwise, the NATO alliance will have one leg, which is very small, and maybe the other leg is very big, so it will be unbalanced. And I think so. We have a double need to optimize our investment and our research and development. One, because we should not be fragmented. Second, because we have to be good, strong partners of the NATO alliance. So I think Europe should really seriously consider this. Let's see what happens now with the new commission, of course. This is, as you said correctly, this is not a single country job. What we're trying to do, companies now have a social responsibility because the big companies now, multinational companies, they're talking. So we are talking among the big players. Somehow beyond the states, because we can act like Sherpas, we can act like explorer for alliances. And if the alliances can work, then the states have more capability to say, okay, let's do this together. Companies are not elected, as you know. The politicians are elected. So it's our social responsibility to create a little bit of synergy and collaboration. Not very easy, because we have domestic markets, because we have national sovereignty issues. But this is a social responsibility. What we're trying to do in this month is exactly this. But you touched the key point.
Okay, thank you. Okay, down there.
My name is Wang Lihao. I'm from Northwestern Polytechnical University. I'm here.
I can't see anything. I'm sorry. I'm
He's,
almost blind.
He's up there to the left.
Oh, yeah, thank you.
Yeah. And now I'm studying for a PhD. Thank you very much for your speech. My question is, do you think AI will replace almost all traditional industries in the future? And can AI have complete physical interpretability? Thanks.
No, look, I'm maybe romantically convinced that humans will be needed. I believe that AI will be a powerful tool, very powerful. In the most optimistic description, will give us more time to do serious things and difficult things, and will be doing very effectively routine actions, optimizing industrial processing, optimizing public administration. This is the only way I can see AI to be used correctly in the advantage of humanity. Maybe we're influenced a little bit too much by science fiction movies, but I don't think, as I said, you can switch off the computer anytime. There's a button, you close it, and the AI is shut down. I think it will be a very powerful tool. The point is how we educate citizens, everywhere in the world to use the digital tools, today there is a big confusion because people are thinking that the social media, the social are AI, the social are nothing. I mean, this is just a free commercial point where you think it's free, but the product is you. So this big confusion means that Western citizens are not aware that digitalization, AI, and those technologies have to be understood properly. So maybe the school, the university, the media should explain this properly. Maybe I'm too dreamful, but I think that is the key point.
Okay, thank you very much. We have to now congratulate Roberto for this prestigious award and for his wonderful presentation. We want to thank you so much for taking time from your busy schedule to be here with us. I have a little medallion on behalf of ICAS to remember this occasion, and the certificate, and Erasmo has also a little present from Aida.
Thank you very much.
And I guess we have a photographer here.